right, we're going to begin open book test 4142, and chapter 4 is integrating, which integration is the opposite of finding the derivative. This is called an indefinite integral, which means that we're going to write an equation. We're not going to find the integral within a specific region. That's something that we'll do later. So we're just going to learn how to find the integral and then go back and check by differentiation, okay? So let's just kind of make an example first, just so we can kind of get this in our mind. If we had something like 2x to the third, if this was f of x is equal to 2x to the third, and we wanted to find the derivative, what would the rules be? And I'm going to color code this so we can see it. The rule would be to do what?
Multiply the exponent by the
So exponent times coefficient, and then
subtract the exponent.
we would subtract 1 from the exponent. So we multiplied first, we subtracted second, and then we would have x squared. Well, integration then would have to be opposite, right? The integral would have to be opposite. So if we did the integral of 6x squared, then we would do the opposite of subtraction, which is to add first, and then the opposite of multiplication, which is to divide second. So we would do addition and then division. So we would do the opposite of subtracting 1 from that exponent, which is to add 1 to the exponent. And then we would do the opposite of multiplying by dividing. And when we do that exponent, 1 plus 2 equals 3, then that's going to be my new exponent. But I'm also going to divide by that same 3. Okay? So, again, we're going to be reversing the derivative. The last thing that happened in the derivative was to subtract 1. So the first thing that happened in the integral is to add 1. When you add 1, you're going to get a number for the exponent, x cubed. And then we're going to do the opposite of multiplication, which is division. And we're going to divide by that same exponent. So you can see that those are going to match up. Okay? So we add 1 to the exponent, divide by that exponent. And then you can see that the 6 and the 3 would reduce to a 2, and we get 2x cubed, which is where we started. So there's the basic idea of integration. And you probably realize maybe that I should have had a dx. I should have had a dx there when I began. Okay? Because we have to write what we're differentiating in terms of. Okay, the variable of differentiation. Okay, so when we look at this situation then, we have the integral of x plus 3 dx, and we know that the integral of a sum is the sum of the integrals. We could rewrite this as the integral of x dx plus the integral of 3 dx. Now, the integral of x, if we think about what we need to do, we need to take that exponent of 1, and we need to add a 1 to it, which is going to give us a 2. So we would have x squared, and then we would divide by that same 2. And then we would have plus some constant c, right? Now, when we find the integral, what have we found? The integral takes us back to the original function f of x, because this is f prime of x, right? So we're doing the integral of the derivative, which takes us back to the original function. And then we would have plus, what is the integral of that constant? Well, we have to realize that there's an understood x to the 0, right? So we would have to add 1 to that, which would give us a 1. And then we would have to divide by that same 1. So we're going to have 3x to the 1 divided by that same 1. And then a plus c. That's if we write it out as derivative of the sum. So we have f of x is equal to x squared over 2 plus 3x, and then we still have just 1c as we look at it. You don't have to put plus c. We just have one constant c. Okay? But see how we went from the derivative back to the original function using the integral. Now, it says to check, so we want to check this by taking the derivative. So we want to take the derivative of the original function and see if we end up with what we had to start with. So to take the derivative, remember we take the exponent times the coefficient, and so we would have 2x, and then we would reduce the exponent by 1, and so that would just leave us x over 2. And then on this one, we would multiply the exponent times the coefficient, which would give us 3. Reduce the exponent by 1, which is 0, so we then have just a constant. And then we have plus c, and we know the derivative of a constant is 0, so the constant goes out. Something went out before, we didn't know what it was, but so that constant went out, and the 2 over 2 is 1, so we have x plus 3. Which takes us back to where we started, and so we have proven that the integral is correct by taking the derivative and working our way back. Any questions on number 1? Okay. Number 2. Now, on the first one, I separated it into pieces, and maybe we should do that for a little while. It's probably to the point we don't need to separate it, though. With our integral, we know that the integral of the sum is the sum of the integrals. The derivative of the sum is the sum of derivatives. And so let's just integrate each part then without splitting it apart first. We're going to take the 3 exponent, we're going to add 1, which is going to give us a 4. So that would give us an x to the 4th divided by that same 4. And then on that 2, there's an understood x of 0, x raised to the 0. So we would add 1 to that, which would give us a 1. So we've got plus a 2. We've got an x that we now have raised to the 1 divided by that same 1. And then we cannot forget to put a plus c. So my f of x, my original function, comes back to here. Simplified, we have f of x is equal to x to the 4th over 4 plus 2x plus c. Okay? Let's see if we got that. We want to verify by taking the derivative. To take the derivative, we're going to multiply the exponent times the coefficient, which will give us 4. We're going to subtract 1 from the exponent, which gives us 3. We're going to take the exponent times the coefficient 2. Reduce the exponent by 1, which gives us an exponent of 0. So we just have the 2, and we know that the derivative of 2x is 2. And then the derivative of a constant is 0, so that goes out. So we have f prime of x is x cubed plus 3 plus 2. And we verified that that's what we started with there. Okay? So we found the integral, which took us from the derivative back to the original function. And then we did the derivative to verify. Okay, any questions on number 2? All right, number 3. We're going to want to rewrite this in exponential form so that we can use our exponent laws to solve. So we'll rewrite this as the integral of the cube root is the third power, right? So this would actually be x to the 2/3 power. Okay, the cube root squared dx. And so our rule is to do what? Add 1, but we're going to put it in terms of thirds, so that would make that 5/3. And so we're going to have x raised to the 5/3 divided by that same 5/3. Now, I'm just going to write this here. When you divide by a fraction, what do you really do? Multiply by the reciprocal, so it's really going to look like that, right? When you divide by 5/3, you're really multiplying by 3/5. And then we need some constant c. So we're going to have f of x is equal to, if we write this properly, we will have 3. We're going to have the cube root of x raised to the 5th power, and then plus that over 5, and then plus that constant c. Okay? So we got that. Now, I'm going to take the derivative. I'm going to take the derivative from here because it's in exponential form. So if I were to take the derivative of this to go backwards, f prime of x, then I would need to subtract 1, which would put me at, I'm sorry, I don't need to do that yet. I need to multiply the exponent times the coefficient, right? So I would have 5/3 times the coefficient 3/5. I'm just going to write it like this. Okay? So exponent times coefficient. And then we're going to take our variable. We're going to reduce the exponent by 1. So it takes us from a 5/3 down to a 2/3 on the exponent. And the derivative of that constant c goes out. These cancel. And so we're going to have x to the 2/3, which is the cube root of x squared, which matches what we had to start with. Okay? Any questions on number 3? All right. Number 4. We do not want to integrate a quotient. So to make it to where we do not have to integrate the quotient, what can we do? We can distribute. Now that's x to the half, so I'm going to go ahead and write that square root as x to the half if that's okay. And then we're going to distribute it. Now I'm going to go ahead and write this out if that's okay. We're going to have x squared divided by x to the 1/2 plus x to the 1st divided by x to the 1/2 plus 1 divided by x to the 1/2. Is it okay if I write it all like that? Just so we can see. I don't want us to make any mistakes in case somebody may need to rethink their exponential law. Remember, when you divide with like bases, you subtract the exponents. So 2 is 4/2 minus 1/2 is 3/2, so that becomes x to the 3/2. So this x squared divided by x to the half turns into x to the 3/2. When you divide with like bases, you subtract the exponents. Okay? So we're going to do this. When you divide with like bases, you subtract. That 1 is 2/2 minus the 1/2 leaves us with 1/2. And so we have plus x to the 1/2. We're trying to write them in exponential form as a sum. And then what's 1 divided by x to the half? How do we write that?
It'd be 1 over x squared.
It's like 1 over x to the half, but how do you write that with it on top?
X to the negative 1/2.
There you go, x to the negative 1/2. Now, how can we write this? 1. What's 1 the same as if we write it in terms of x, just so we can say we did this? That's really x to the 0, right? Because anything to the 0 power is 1 divided by x to the half. And when you divide with like bases, you subtract, so 0 minus a half is negative 1/2. You see how we could have thought as that x, as that 1, as x to the 0, and then we could have taken care of that. Okay, so, and then we have, I should write this properly, parenthesis dx, right? That's more properly written. Okay, now we're going to integrate the parts here. So we would add 1, so we're going to be adding 2 halves to that 3 halves, which is going to give us 5 halves. And so we're going to have x to the 5 halves, right? But then we need to divide by that 5 halves. And how do you divide by a fraction? Multiply by the reciprocal, okay? And then plus, we're going to add 1 to the exponent. We have 1/2 plus 2 halves is 3 halves. So we're going to have x to the 3 halves. And then we're going to divide by that 3 halves, which is same as multiplying by the reciprocal 2/3. And then plus, we're going to add 1 to the exponent. Negative 1/2 plus 2 halves is positive 1/2. We're going to have x to the positive 1/2. And then we're going to divide by that 1/2, which is the same as multiplying by the reciprocal 2. Now, we're taking the integral, so we're going from the derivative back to the original function, right? So if we write this as radicals, we're going to have f of x was 2 square roots of x to the 5th over 5 plus 2 square roots of x to the 3rd over 3 plus 2 square roots of x. So that would be the original function. Plus, I almost forgot, c, right? Plus c. I need to put a plus c right there. Don't let me forget my plus c, because if you forget, I'll count it wrong. We still got that. Now I'm gonna wipe out the bottom line because we were wanting to verify, and we'll verify that from the exponential form, not the radical form. So we're going to go back and verify that with differentiation. So what we would do is we would take the exponent times the coefficient. So that would be 5 halves times 2 fifths. Reduce the exponent by 1. So we take 2 halves away from 1 whole, 2 halves away from 5 halves, leaves us with 3 halves. And so that would be x to the 3 halves. And then plus exponent times coefficient. We're going to have 3 halves times 2 thirds. Reduce the exponent by 1, which leaves us with a half. So x to the half. And then plus exponent times coefficient x reduced by 1 gives us negative 1/2. And the constant goes out. And so we're going to have f prime of x is, those go out, x to the 3 halves, which is the square root of x cubed. Those go out. plus x to the half, which is square root x. Those go out, and we have x to the negative 1/2, which is going to be 1 over square root x, which is an equivalent form of this if we factored out or found a common denominator, okay? So we could mess with that until we made it in the same form it was to begin with. Any questions on number 4? Okay? All right, number 5. Number 5, we have a product, but right now we know that the derivative of a sum is the sum of the derivatives, and the derivative of the difference is the difference in the derivatives. We know how to use the product and quotient rule with differentiation, but we've not talked about how to integrate if there's a product or quotient. And what we do is we're going to go ahead and write it as a sum or difference. So we're going to have to FOIL this out, as we would call it, multiply these binomials. You will distribute the x and then distribute the 1. I'm just going to go ahead and expand it. If we went x times 3x, we would have 3x squared. X times negative 2 is negative 2x. And then the 1 times 3x is 3x. And 1 times negative 2 is negative 2. And then we combine our like terms. We have 3x squared plus x minus 2 combined dx integral. So we multiply the binomials, and now we will treat it as a sum. The integral of the sum or difference is the sum or difference of the integrals. So again, you would add 1 and then divide by that new exponent of 3. And so if we can just maybe streamline now, those 3's are going to cancel, as you see, and we're going to have x to the 3rd. Here, we would take that 1 and add 1. That would give us a 2. We would divide by that same 2, and so that's going to give us an x squared over 2. With this 2, there was an understood 0, x to the 0. We're going to add 1, which would give us a 1. We would divide by that same 1. And that's going to give us a negative 2 over 1, x to the 1st. Plus that constant of c. Okay? Let's see what we did that. So if we were to integrate, take the derivative then to verify, then we would take exponent times coefficient, 3, reduce the exponent by 1, x squared, exponent times coefficient, 1/2, 2 times a half is 1 understood, x, subtract 1, and we have x to the 1st. We have an understood exponent of 1. We're going to take exponent times coefficient minus 2. We're going to reduce the exponent by 1, 0. X to the 0 is 1, and the derivative of constant goes out. We have 3x squared plus x minus 2, which is what we had when we multiplied the two binomials. Okay, so we have found the integrals, and we verified by taking the derivative. When we had a quotient, we distributed to create a sum or difference. When we had a product, we distributed to create a sum or difference. Any questions on the first 5? Okay. The next examples that we have are some trigonometric examples. We have a sum there, and recall again that the derivative of a sum or difference is the sum or difference of the derivatives. And what we're having to think is, where did this come from? Where did this come from? Well, what is it that has a derivative of something with a sign in it? Okay, now let's think about this. If I had f of x is cosine x, then what would f prime of x be? negative sine x. So if this is positive, then the original had to be the opposite sign. See that? So what would the derivative of the first part be then? The integral of the first part be? Good. It needed to have come from a cosine, but because there's a sign change when you take derivative of cosine, if I need it to end up positive, then I needed it negative to start with. Good. Now, if I have an original function that's sine x, what is the derivative of sine x? Well, it's cosine x without a sign change, right? So there's not a sign change on the second one, 3 sine x, and then we need that constant c. So f of x is negative 2 cosine x plus 3 sine x, plus that constant c, right? That's good. Okay. Now, if I were to find the derivative then, we know that the derivative of cosine is negative sine, so we have a negative, negative, which makes it a positive 2 sine x when we take the derivative. And we know that the derivative of sine x is cosine x. There wasn't a sign change, so plus 3 cosine x, plus 3 cosine x, which is what we had here, so we have verified the integral with the derivative. Okay? Any questions on number 6? All right, well, let's continue this. We'll just do it with the next one. Secant squared. What jumps into your brain when you see secant squared? Tangent. Good. Good. So we know that if we had f of x is tangent x, if we had the derivative of tangent, it would be secant square x. Okay? And so we know that the secant square x must have come from tangent x. We know that negative sine x comes from positive cosine x, and then we need that old faithful plus c. So this would take us back to the original function of tangent x. And I put x, I should be putting theta here. We've got a theta, so let me put it in terms of theta there. And so we have tangent theta plus cosine theta plus that constant of c. Okay? To verify, we have f prime of x. The derivative of tangent is secant squared. The derivative of cosine is negative sine. And so we went back to our original function. Okay? We've talked about derivative of sine, derivative of cosine. Now we've written the derivative of tangent. Let's go ahead and write the rest. What is if the function was cotangent, what is the derivative of cotangent? Negative. Is the derivative of cotangent is negative cosecant squared. Okay. And then what is the derivative, if we had secant x, what is the derivative of secant? Secant, let's do that. Secant x, tangent x. And what is the derivative of cosecant x? Good. Negative cosecant x, cotangent x. So there's the rest. We know that the derivative of Sine is cosine. I'm just going to go and write these in here too. The derivative of sine x is cosine x. The derivative of cosine x is the negative of sine x. Okay, so there's our basic trigonometric derivatives, in case you need those in your notes. And so we're just thinking backwards when we're integrating, okay? All right, any questions on number 7? Okay, number 8. Number 8, tangent square y plus 1. Tangent square. What is it that has the derivative of tangent square?
Secant.
But the derivative of secant was, the derivative of secant was secant tangent, right?
Yes.
There's not one. So what do we do? Well, we've got to think about things from the past, right? Tangent square plus 1. Does that look like anything you've ever seen before in your life? Well, remember the Pythagorean triplets? Some of them anyway? The Pythagorean identities, excuse me. Pythagorean identities. I was jumping back into geometry class. The 3, 4, 5, and the 5, 12, 13. The Pythagorean identities, the most basic one we know is that sine square x plus cosine square x is equal to 1, right? And we can rewrite that as 1 minus sine square x equal cosine square x. There's a lot of different forms, okay? Do you remember the Pythagorean theorem, that the identity that involves tangent square? Okay. So secant square is equal to tangent square plus 1. Secant square equal tangent square plus 1. And then we also know that cosecant square is equal to cotangent square plus 1. Okay? So secant square is equal to tangent square plus 1, and cosecant square is equal to cotangent square plus 1. Sometimes it'll say 1 plus tangent square, or 1 plus cotangent square, but we know that that doesn't make any difference. So those are your Pythagorean identities. So by a Pythagorean identity, we can replace that with secant square. That makes it look a whole lot better. We can replace that with secant square. And so we're going to have the integral of secant squared y dy. And what is it that has a derivative of secant squared? Tangent. So the integral of secant squared y dy is tangent y plus that constant c. Okay? So we changed tangent square y plus 1 into secant square y with a Pythagorean identity, and then that gave us something that we knew how to take the integral of. We knew something that had a derivative of secant square, and that something was tangent y. Okay? So there's my original function. And then if I wanted to find the derivative of that to verify, I would say, well, what is the derivative of tangent y? Well, it's secant square y. And the derivative of the constant goes out. And then we can make that Pythagorean identity substitution again and take us right back to there. Okay? Any questions on number 8? So be aware that when you get into the trigonometric integrals, that you have to remember all of your identities. And you have a sheet with those on it, and we need to study that sheet. I'm having to look a few of those up occasionally. And remember, when I first got to that problem, I'm like, we don't know how to do that. We don't know how to do that. What do we do? You know, and I think, okay, well, this is trig. We got to think trig. So remember to remember. All right. Appreciate your attention. We'll stop there, and we'll do the second part next time.